my name is Kai Bongs. I'm a professor at the University of Birmingham and the director of the UK National Quantum Technology Hub in Sensors and Metrology, which is part of the UK National Quantum Technology Initiative to get fundamental science into the market with the example of quantum technologies. Our hub is consortium of 6 universities. It's led by University of Birmingham and has University of Glasgow, Nottingham, Southampton, Strathclyde and Sussex as partners, in addition to about 70 companies engaging with us on producing quantum sensors, but also mostly on the end user applications. So the UK National Quantum Technology Initiative is covering all quantum technologies which are identified as being ready for translation. So there are 4 flagships as the projects for hubs. The hub led by University of Birmingham is about quantum sensors and quantum metrology. The hub led by the University of York is about quantum communication. The hub led by University of Oxford is addressing quantum computing or networked quantum information. And the hub led by the University of Glasgow is about quantum imaging. So the goal of the National Quantum Technology Initiative is to create an ecosystem to have a quantum technology industry emerge in the UK. So it's not about science, not about developing novel concepts, novel science research, but really to translate existing results into a technology and enabling companies to flourish, which means we produce the skills. We have, of course, we train PhD students who then know about how to do the quantum technologies, but we are also addressing skills in engineering and other disciplines, because in the end it will be engineers in the end user companies who have to use the quantum technology. So educating them is very important there. The other part is that we are creating the underpinning technology. So at the moment you can build quantum sensors very well. You can go to the lab supply stores, you buy tables full of individual discrete components, put them together in a year's PhD time, and you have a working quantum sensor which beats classical devices. But it's not anything you would like to put into industry. So you need OEM type modules for the lasers, for the vacuum systems, for the overall control system. And this kind of infrastructure is what we're installing. So we're working in our hub with the Glasgow Nano Center to produce laser systems on a chip, so to have an entire system integrated on the chip, which replaces with a few hundred or maybe a few thousand pounds, something which is tens of thousands of pounds worth of laser systems from a research supply. Similarly, we are working with E2V as a vacuum electronics company who has 5 decades of experience in doing vacuum electronics, which means brazing vacuum chambers, sealing them in a way that they stay under vacuum, 10 to minus 9 millibar or better, for 20 years on the shelf without a pump attached to it. And this is exactly what we need to get away from the current CF flange, ion pump technologies, which are quite cumbersome if you wanted to put it into a piece of technology. So we will encourage spin-offs where they make sense, but it's also engaging companies with existing know-how to have them bring their know-how into quantum technologies. For instance, the vacuum electronics, where the know-how of how to do vacuum chambers which are sealed and self-confined is existing in industry, so we just have to make that industry interested in working with us. While in producing quantum sensors and doing the prototypes, there might be a route which is more suitable to a spin-off or small SMEs to say we will engage in this. But definitely we are also very happy to work with companies, larger companies who want to be component or subsystem manufacturer in this. The vision of taking quantum technology to market is about 20 years because obviously technology translation is not a quick thing. We will have a 5-year dedicated program of funding now. So we have the 270 or 300 million right away to do the first step, but we're currently discussing the next steps in this program and how the funding will evolve. It makes sense to have the funding in chunks of a few years because the start of the program is heavily focused on universities and getting universities to engage with industry to get the first step in getting the technology out. If we are successful, the next step should ideally be more focused on industry, because then industry should be sufficiently engaged to take on quantum technologies and essentially dictate more where they see the economic potential for it and have the program steered by that. The main applications of quantum technology will be quite disruptive because it enables things which are not possible at the moment. There are also some evolutionary technologies, but most of this will open up completely new possibilities. So of course, for instance, if I speak from my area of gravity sensors, there are gravity sensors existing, classical ones, which are used in underground surveys. So it will be partly an evolution of making better and more versatile sensors and maybe cheaper sensors. But we also can see that once these sensors become a bit cheaper, that there will be a mindset change in the industry, because currently civil engineering surveying companies, they call in gravity surveys once something has gone wrong. So they usually start with developing a field by doing a few test drills, and if any of these test drillings hits a void or hits a problem, they say, we better get gravity in. And then the gravity survey usually takes weeks to complete, because the current technology is relatively slow and it takes a few minutes to take a measurement point. While with quantum technology, if you move that into a few seconds per measurement point, you are at the disruptive edge where it might become a standard technology, which you do before you do any other development. And so that would be a big change to the market.